So as a reminder, activity is the way that we take into account the non-ideal behavior of our solution. So if we have an ideal solution that follows Raoult's law, right, the vapor pressure is equal to a mole fraction times the pure vapor pressure of the substance. Right, that's not usually going to be true for most of the things that we look at. We usually have non-ideal behavior. And if Raoult's law is followed, we get that the chemical potential of, and for 1, we're going to call, our solvent will always be component 1 in these sets of videos. So mu1 is equal to mu1 star plus RT natural log of P1 over P1 star. This is an equation that we derived in the previous chapter. And if we plug in Raoult's law, that gives us, we have mu1 star plus RT log x1, because the P1 stars will cancel. And as a reminder, activity is a way to sort of preserve this sort of form of the equation, where we substitute for x1, we instead have a1 here for substances that do not follow Raoult's law. And we define a1 is equal to P1 over P1 star, right? So that it directly follows this equation here. Okay, and so we can say that for our solvent, our chemical potential is given by mu1 equals mu1 star plus RT log A1, where A1 is defined as the actual vapor pressure divided by the pure substance vapor pressure. Okay, so solvent, that's pretty straightforward. That's how we can define activity. That's how we can find activity. If we can measure the vapor pressure of our solvent in the solution, compare it to what it would be if it was a pure substance, we can actually calculate the activity pretty straightforwardly that way. Solvent, so that's the solvent. The solute is a little bit more complicated. So there we need to use Henry's law. So as we discussed in the videos about non-ideal behavior, if the solvent is following Raoult's law, the solute is following Henry's law. And as a reminder, Henry's law says that the vapor pressure of component 2 follows this equation, where we have some Henry's law constant, some linear coefficient here, times the mole fraction of component 2. And again, component 2 is equal to solute, and we will just consistently use that in this set of videos. Okay, so by definition, we can say that, okay, the chemical potential of component 2 in the solution is equal to mu2 star plus RT natural log of P2 over P2 star. All right, this is just, again, this is the definition of chemical potential that we derived in the previous chapter. Now, if we plug in Henry's law for P2 here, instead of Raoult's law, we'll get mu2 solution is equal to mu2 star plus RT natural log of KH2 divided by P2 star. And I'm going to separate out the second term. We have it, right, so we have this x2 term. We're going to separate out R2 log x2. So this is just, we can separate out the logarithms. If we have natural log of x times y, we can write that as natural log of x plus natural log of y. So that's how we separated out these two terms. Okay, and so what we do is we define our activity. Again, what we want, we see this RT natural log term here, and we'd like to substitute the activity here, right, so that we preserve this sort of RT natural log of a concentration of some kind. And so we define the activity such that we substitute, where we have x2 here, we substitute the activity. So define A2. And so the activity for solute and activity for solvent are not defined the same way. So that's something to make very clear here. So mu2 for our solution is equal to mu2 star plus RT natural log of KH2 over P2 star plus RT natural log of A2. So in the case where we have deviations from ideal behavior, the activity captures that, and we get this overall. overall equation. Now we want to define our standard here, so mu2 star. We define it such that mu2 star is equal to mu2 star is equal to this whole thing plus RT natural log of KH2 over P2 star, meaning that this second term goes to 0. This is what we call our standard state. Now this may not be an actual state. This is like a hypothetical standard state. But our standard state is where the Henry's law coefficient is equal to the pure component vapor pressure. Okay, and so overall that gives us an equation for the activity that, or for the chemical potential in terms of the activity, is that mu2 in our solution is equal to mu2 star plus RT natural log of A2. Right, and so we have an activity that looks very similar, right, to what it is for a solvent, but how you actually find that activity is very different. So we define A2 in this case is equal to P2 over KH2, and that lets us write this equation this way. Okay, and so just to follow up, I think I won't make a separate video of this because it's just a really quick thing. This current way that this is defined is in terms of mole fraction. So this is all in terms of mole fraction. And we can rewrite this in different concentration terms. So this activity written in terms of mole fraction, we actually call A2x to indicate that it's in terms of mole fraction. It's equal to P2 over KHX, emphasizing that the Henry's law constant is relative to mole fraction. We can also do this in terms of molarity or molality. And so we define those as A2C, this is molarity, as our standard state. And basically this is just what units the Henry's law constant is expressed in, and what our activities approach as we go to ideal behavior. So we can define A2C, where we have P2 over KHC, where things are expressed in molarity. And in this case, the activity of component 2 approaches the concentration in molarity, which we write as C, as that concentration approaches 0, so as we get closer to ideal behavior. In this, right, for our mole fraction, it's instead that A2x approaches the mole fraction as the mole fraction goes to 0. And we can also define this in terms of molality, which we write A2m is equal to P2 over KH written in molality units, and same limiting behavior. At low concentrations, this approaches the molality, which we'll write as m, or we can also write it as a kind of cursive m, as the molality approaches 0. So these are the different types of standard states that we can define, and it's really in terms of how we express the Henry's law constant and what we want our limiting behavior to look like. The one that's probably used the most often is this one here, because we like to use molarities as chemists, but we can use any of these.